Assalamu alaikum. Welcome back. Any network performance evaluation study is going to create a lot of data, and as a performance analyst, it is our job to extract meaning from all this data. Data, because of its size, can overwhelm any person, and a performance analyst has to use appropriate tools which are suitable for the kind of data he or she is analyzing, for summaries which help the stakeholders in making important decisions. So I'm going to talk about two things today. Firstly, I want to talk about types of data, and then I want to talk about, for all these data types, what scales of measurement exist for making measurements for all of these data types. Also, I want to talk about how do we specify the overall patterns of data. So there are many important aspects of data. For example, what is the data distribution? Where is the data centered? How much variation exists in the data? What meaningful associations exist amongst variables in this data? So we're going to see all of this in this session. We begin with the first part, which is going to deal with types of data and types of statistics, because we need specific types of statistics to deal with specific types of data. We'll be seeing that not all kinds of statistics are applicable for all data types. So we need to be very careful here. So a very broad distinction that we can make between types of data is to classify them into two categories: qualitative and quantitative. In qualitative data, our description of data and our distinction of data depends on measures of variables done on the basis of quality rather than on quantity. In other words, we simply apply labels or categories to data, and we do not give them numerical measures. This is useful in many cases where it's difficult to give a number to a certain measurement, but for example, we can classify them into a set of categories. So we start with qualitative data first, and then I'm going to talk about quantitative data. Initially, qualitative data would be described, and we know, I've already mentioned that qualitative data, the measurement is done on the basis of quality and not on the basis of quantity. So for qualitative variables, you cannot measure how much of that exists. You can only know subjective measure of that. So it's important to understand the scales of measurement for such data, and essentially there are two scales of measurement. The first one is known as the nominal scale. In the nominal scale, which comes from the root word of just name, so nominal follows from name, हम हर data variable को कोई एक नाम दे देते हैं, but then we cannot compare the different labels. So as an example, we may describe the data as belonging to different categories. We may say that the data packet traces that we have contains packets that have TCP as their transport layer protocol or UDP as their transport layer protocol. This TCP and UDP describes something about the data, but this is describing just the quality of data or giving just labels to the data. We're not measuring something in numerical terms. Nominal scale ke alawa, there is another scale which is a little more advanced in that it gives us some more information. So in an ordinal scale, we just do not give labels to it, but the labels that we give to it also have a sense of order amongst themselves. Example of this is the Likert scale, which is very common in social sciences research. So you might have seen some survey papers in which you are asked question, and they ask your opinion about particular things, and they ask you to rate your answer on a scale of 0 to 4, where 0 may mean strongly disagree and 4 may mean strongly agree, and the numbers 0, 1, 2, 3, 4 all fall in this scale. So we have a sense of order. So we would know that 4 is more agreeable than 3, or it's more agreeable than 2. But how much more agreeable is it? The scale itself does not tell us. It is only telling us the order. Another example is the grade system in which you give later grades to a student on his performance in a particular course. So for example, if a student performs very well, he would have an A grade. A student performing less well would be having a B plus. Even less well would be having a B. A student who performs worse than B is going to get a C, and so on. These letters, while they tell you the relative order, they do not tell you by how much these students differ. यानी कि letters के बीच में कितना difference है, that may differ for different variables. So the difference between A and B plus may be more than the difference between B plus and B. So because of this, we cannot, do general statistics on qualitative variables. For example, taking an average may not be meaningful. Distances along the scale may not be meaningful, but the order along the scale is meaningful. अभी हम बाद में देखेंगे कि for such variables we have special kinds of statistics known as non-parametric statistics, in which we have designed the whole framework around dealing of nominal and ordinal data variables. Apart from qualitative variables, we also have quantitative variables, and this is where a network performance analyst would be really interested in, because almost all of the metrics that we are interested in are going to be quantitative. In quantitative data, the description and the distinction of data is measured on the basis of quantity. So you're measuring something in amount of some number. So this actually characterizes what a quantitative variable is. और इसको measure करने के लिए भी दो scales हैं. The first scale is known as the interval scale. The second scale is known as the ratio scale. In both of these scales, we're measuring the variable we're interested in terms of number. एक इसमें subtle difference है. आमतौर पे इसको इतना emphasize भी नहीं किया जाता, लेकिन we need to understand this because we need to apply proper statistical tool for particular data types. जो interval scale होता है, it has ordered labels, यानी कि it is more stronger than जो अभी हमने पहले पढ़ा था ordinal scale की measurement. It is more stronger than that, in that it has the property that all the labels are ordered. Furthermore, it has the property that the distances are meaningful. So जो successive labels आ रहे हैं उनके बीच में जो distance है वो भी meaningful है, but it does not have an absolute zero. चूंकि इसका zero arbitrary है, उसको आप ऊपर नीचे कर सकते हैं, आपने खुद define किया हुआ है, इसमें हम ratio को इस्तेमाल नहीं कर सकते. तो उसके अलावा we can do all sorts of statistical, we can use all statistical tools on this, but we cannot use the ratio. An example of an interval scale measurement is temperature measured in Fahrenheit or in centigrade. So now जो 0 degree से लेके 10 degree तक measurement है, it's the same distance as the measurement distance between 10 degrees and 20 degrees. लेकिन we cannot say if something is twice the size of the other because the zero that we have is arbitrary. Centigrade में it's defined differently from how it is defined in Fahrenheit. And also in these scales, interval scale की बात हो रही है, zero measure does not mean total lack of something. So if you have a zero value, it does not mean that you do not have any temperature or any hotness or coldness. It just means that you are coming at a value which we've defined arbitrarily to be zero. Lekin if we have an absolute zero, and you may think of temperature measured on the Kelvin scale in this as an example of this, then zero is the absolute lowest value that you can have. And because now we have a baseline, now you can do comparisons. So you must note here कि अगर आपका zero arbitrarily set है, उसको आप ऊपर नीचे कर सकते हैं, तो ratio फिर meaningful नहीं रहता. लेकिन if your absolute zero is defined in a rigid sense, then your ratios become meaningful. All the performance metrics, almost all of them that we are interested in, would fall in the category of quantitative variables, and most of them would be measured on a ratio scale. Example would be throughput, delay, packet loss, packet size. So packet size इसके एग्जाम्पल को थोड़ा और हम एक्सटेंड करते हैं. A zero size packet is meaningful because you cannot have a packet having negative size. तो इसका चूंकि zero well defined है तो हम ratios भी ले सकते हैं. Packet size of 100 bytes would be half the packet size of a packet having packet size 200. So in this sense ratios become meaningful. और इसके लिए for such quantitative variables जितने भी हम statistics इस्तेमाल करते हैं आमतौर पे जो हम इस कोर्स में भी पढ़ेंगे, they are all applicable, but all of them are not applicable for qualitative variables. Also, let me again describe the types of different statistical frameworks that we have. So, and they are relevant to the data types that we've studied. The first kind which I'm going to tell you about is parametric statistics, and this is the most common framework of statistics. आमतौर पे जितने भी हम tools पढ़ते आए हैं, undergraduate study में पढ़े हैं या आमतौर पे जो apply हम करते हैं, those are examples of parametric statistics. An important insight that we must not ignore is that all of these statistics is based on an assumption. So mostly whenever you're making use of such tools, उसके पीछे काफ़ी strong assumptions हमने ली हुई हैं. So if those assumptions are met, we are okay to be using these tools. In most cases, these assumptions are not met. In some of these cases, जब ये assumption नहीं meet हो रही, तब भी आपका काम approximately चल जाता है. But you must know that your assumptions are not being met. Because in certain cases, when the assumptions are not met, your approximations are going to be way off mark. कुछ assumptions जो कि parametric statistics में हम लेते हैं, आमतौर पे हम सोचते हैं कि your data is normally distributed. So if you have a sample, तो आप देखेंगे या assume करेंगे कि you have approximately a normal distribution, और जो आप samples ले रहे हैं वो independently drawn है from populations having consistent variances. तो ये independence की जो assumption है, this is a strong assumption not met in many practical studies, and we must be taking care to ensure कि independence हम ensure कर सके. Independence का मतलब है कि अगर आपने एक measurement ली है तो उसका कोई effect अगली measurement पे as such नहीं होना चाहिए, because if that is the case you would be having biased samples. So usually it is assumed that all your values measurements are independent, those are not biased. Non-parametric statistics में हम कम assumptions लेते हैं, इस वजह से हमारी जो analysis है, जो हमारे results हैं वो less powerful हैं. Because for example parametric statistics में if we assume a normal distribution with a known mean and given variance, we'll be talking about these terms soon in this course, but for now जो आपका common notion है mean का और variance का, उसको हम लेके चलते हैं. If we know this, normal distribution के कुछ interesting rules हैं, so उसके हिसाब से आप infer कर सकते हैं कि most of your data would be within this range of the mean. Within a longer range you would have more data, तो इसके particular values आप state कर सकते हैं. So this is obviously more powerful. But in non-parametric statistics, we do not make use of mean and variances. We do not assume that you have a normal distribution, and we then see what can we do. तो वो कुछ tools ऐसे इस्तेमाल करेगा, कुछ measures ऐसे इस्तेमाल करेगा which are not dependent on particular distributions, and those tools do not make meaning only for particular distribution. वो ज़्यादा general है. तो ये distinction important है. और एक और चीज़ इम्पोर्टेंट है कि जब आपके पास नॉमिनल और ऑर्डिनल स्केल पे मेजर्ड वेरिएबल्स हों तो आमतौर पे हम पैरामीट्रिक स्टैटिस्टिक्स उस पर इस्तेमाल नहीं कर सकते. उसके लिए नॉन पैरामीट्रिक स्टैटिस्टिक्स वुड बी मोर अप्रोप्रिएट. यू वुड बी यूजिंग मेजर्स लाइक मीडियन, द मेजर विच वी डिस्क्राइब्ड अर्लियर. उसके अलावा और कुछ ये टूल्स इस्तेमाल करता है विच वी बी कवरिंग इन दिस सेशन. So with this distinction of data types and of the kinds of statistics, I'd like to move on now to the next part of this session. Let us now discuss how we can summarize the overall pattern of data. As mentioned before, data is often produced in copious amounts. which means the data is produced in large quantities. How is a network performance analyst to extract meaning from all of this data? The need is to have some summary measures which can give you quick insights about how the data is. And for today, we are going to focus only on the summary of data in one variable. The data set may be containing multiple variables, and there may be interesting associations between these variables. But that would be a topic of another session when we talk of regression and correlation. So with this assumption that we're talking of a single variable, what are the things, or what are the summary measures which can help us summarize the overall pattern of data? So the first thing here is the distribution of data. That actually tells us what values are present in the data. So we have different forms of representing the distribution of data. These are the bar graphs, the histograms, and the probability density curves. Furthermore, the second measure I'm going to talk about is the shape of the distribution. So sometimes you have a distribution which is symmetric around a central point. At other times you have skewed distributions, which mean that on both sides of the center you don't have mirror images of each other. You would have values which are far away from the center on one side of the data, but perhaps not on the other side. So we need to understand the overall pattern of data, because many of the statistical techniques depend on some assumptions. For example, they may assume normality of data, that the data is like a normal distribution, which is a symmetric distribution. But if your actual data is asymmetric, you will not be able to apply those parametric techniques which depend on the assumption of normality. Furthermore, we also need to define the center of the distribution. So we've defined the measure of a distribution and its shape, but we need to define a measure of its central tendency. And this is a common pitfall that many network performance analysts choose the wrong measure of central tendency. So we'd be describing that there are actually multiple measures of central tendency, and the choice of the appropriate metric depends on the task that you're performing. Lastly, an important summary measure is what is the spread of the data. So even knowing the distribution of data, the shape of data, and the central point, you may have different spreads of data. The spread of data here means that how far away are the extreme values, and what is the typical variation of data around the central point. So let us now begin our discussion on the distribution of data, in which we try to show the entirety of data. There are multiple ways of doing this, and the choice actually depends on the kind of variable we have. If we have a quantitative variable which is measured either on the interval scale or on the ratio scale, in other words, you have a measurement on the number scale. This may be a continuous variable or a discrete variable, but it has to be a quantitative variable. So a common way of showing the distribution of data is to have a histogram in which the overall range of the values that the variable can take is divided into different bins, and all the variable observations that fall into particular ranges are given to that bin. So you can actually see a histogram shown on the slide, and you see that the range of values are shown on the horizontal axis, and on the vertical axis we can show either the frequency, count, or probability of the variable taking a value in this range. If we are talking of a qualitative variable measured on the nominal or ordinal scale, we can measure, or we can show the overall distribution of data in a bar graph. A bar graph is like a histogram, but in many cases the horizontal axis would have certain gaps between the various values, and that is to indicate that there is no continuum of values between the different values shown on the x-axis, and to also show that these are disjoint categorical variables. So you may imagine, for example, a study in which we are trying to see the some aspect of IP packets, and we can say that IP packets can belong to two different categories, and these can be TCP packets and UDP IP packets. And then we can show the measurements for these particular ordinal variables. In fact, इस case में TCP or UDP nominal variables हैं, because there is no order, no sense of order between TCP and UDP. But you can also imagine measurements on the ordinal scale. So we mentioned the Likert scale, in which you have values from 0 to 4 for various ranges of liking or disliking something. So you can show that on the horizontal axis, and on the vertical axis you can show the frequency, the counts, or the probability. Another common way of showing the distribution of data is to actually show a density curve. And we can imagine this to be the histogram of a quantitative variable in which the bin size is made very small. So you would call the bin size as infinitesimally small, and because of that you have the shape of a continuous curve. And this is also known as the probability density function, the properties of which are that the curve would always be above or equal to the horizontal axis, and the probability of the variable taking a value in a certain range would be the area under the curve in that range. So these are methods of describing the distribution of data, and it's very important that we first of all understand the distribution of data. Something that we have not covered now, but it is perhaps even more important, is to actually graphically plot the data. But we'd be doing this in a separate session when we talk of visual display of quantitative data. So the importance of plotting data cannot be overstated, so we must keep that in mind. In fact, all of today's lecture, when we talk of statistical measures on data, we need to understand that very dissimilar data can give you similar statistical measures. So the first step in the analysis of any networking system should be to actually have a method, or to devise a method of plotting all of the data. And from that, the human brain can actually detect patterns that would be very hard to detect using statistical measures. So the gist of the discussion then is that it is very important to have a knowledge of the distribution of data, and perhaps the best thing that you can do in this regard is to first of all plot the data. Let us now talk about the shape of data. So what are the important questions that we must answer here? The first important question is the data symmetric or asymmetric? Which means, is it symmetric around a central point so that the data would fall on either sides of the central point, with most of the data perhaps falling on the central point, but it's not necessary for a symmetric distribution to have most of the data falling in the central point, as we shall see very shortly. Also, you can talk of the tails of the distribution, which means as we move away from central values, what are the probabilities of having these extreme values? So for some probability distributions, the probability of having extreme values which are away from the center are minimal. But if you have a heavy tail distribution, the probability of having extreme values is non-negligible. Another important aspect is that the density curve, is it single peaked or multiple peaked? Again, parametric statistics actually assumes normality of data, and normal distributions actually have just a single peak and the data is symmetric around it. So we have to observe the data so as to see if our assumptions are being met or not. So let's talk now about symmetric or skewed data. When you have a symmetric distribution, the data on either sides of the center are mirror images of each other. So as you can see in the slide, two symmetric distributions are shown, and the first distribution is not mound shaped. यानी एक पहाड़ी की शक्ल में ये नहीं है, but still because on both sides of the center you have mirror images, you would call this a symmetric distribution. Usually symmetric distributions are also mound shaped, पहाड़ी की शक्ल में, in which the central point has the highest probability of occurring. Examples of such distributions are the normal distribution and the T distribution, which we shall see very commonly in our discussions on inferences. And we can actually show this thing in a histogram as shown in this slide. And mostly because the normal distribution is a theoretical distribution, and we actually have to inspect our data and have to fit the data against the normal distribution to see if our data is approximately equal to a normal distribution. If our data is approximately equal to a normal distribution, then we can actually have a very good time with classical statistical techniques, because classical statistical techniques or the parametric statistical techniques have lots of tools for dealing with normal data that has normal distribution. You can also talk of skewed data. So a data in which real values are on the left side of the center, you would call that a negatively skewed distribution or a left skewed distribution. On the other hand, if the real values are on the right side of the center, this would be a right skewed distribution in which the tail is leaning towards the right hand side. So if you have to answer the question that which side is the distribution skewed towards, you should observe that where is the tail leaning towards, and that would be the direction of the skew of the distribution. An important point is the distribution heavy-tailed or not. And heavy-tailed distribution is a distribution in which extreme values are occurring in non-negligible terms. So this is actually very important for network performance evaluation studies. Whereas most of the data for social scientists is of the normal distribution type, it is more common in network performance evaluation studies to have right skewed data, or data in which you have heavy tails. Heavy tails would mean एक extreme value की occur होने की probability non-negligible है. It's not like a normal distribution in which most of the data would be very close to the center and extreme values are very rare. So in network performance evaluation studies, heavy tail distributions would be the norm rather than the exceptions. जो heavy tail distributions है, it's not necessary that they be asymmetric, because जो हमने Pareto distribution दिखाई है वो right skewed है. Pareto distribution was discovered by an Italian economist, Mr. Pareto, who was studying the distribution of income. And this actually holds very true even today, because in any society you have a lot of poor people, and then you have some middle class people and a few rich people. And because of the few rich people, your mean value would actually be skewed towards the right hand side. But most of the people are actually poor. So a normal distribution would not be a good model for the income distribution of any society, because it's not like the middle class is the most dominant class having the most number of people. Usually the case is that you have more poor people, you have some middle class people, and you have very few people with lots of money. You may also have a distribution which is symmetric around the center, but also it is heavy-tailed. An example is the Cauchy distribution, which is symmetric like the normal distribution, but it has heavier tails. As you can see in the slide here, the tails of the Cauchy distribution are fatter than their counterpart for the normal distribution. The meaning of this is, if you look at the density value, let's say 4 standard deviations to the left of the center, you would see that the density value for the normal distribution is almost 0. But the Cauchy distribution has a non-zero value. And this has a large impact on what kinds of statistics we can do for the Cauchy distribution. So for the Cauchy distribution, actually we don't have a value of mean and variance defined. So depending on the kind of distribution that we have, it may be that we cannot use many of our common parametric statistical tools for them. So it's very important before we analyze the data that we see what kind of shape of data that we have. Is it heavy-tailed or not? Another important aspect is that if you have given distribution of data, is the data single peaked or multiple peaked? So if you draw the histogram of data, the usual shape of distribution, which is normal distribution like, is to have a single peak and which is symmetric around the center. But many of the actual distributions are multimodal, which means they have multiple peaks. This can actually again create problems if you want to create the same techniques of parametric statistic for analyzing such a distribution. And actually such a multimodal distribution is very common in computer networks. As an example, if you observe the packet sizes in bytes in any given network, this graphic is for a particular study, but the general trend is that you have 3 modes or 3 peaks. The first peak would be around 40 bytes, which is the size of an IP packet which has no data, so it's just an acknowledgement. And another peak would occur at approximately 1500 bytes, more or less, which is the approximate size of the Ethernet frame. Because of the dominance of Ethernet as a LAN technology, you would see a lot of packets around this mark. And also you would have a lot of packets having sizes of approximately 576 bytes. This is because this size was defined earlier in an RFC as the size which will not be fragmented when packet traversing through backbone routers. So still many implementations set their packet sizes to approximately 576 bytes. So if you observe this data, you would see that you don't have a single peak. So to analyze this, then we have to see what are appropriate tools for it. It may be that we cannot use our usual parametric techniques for such a distribution. So now we come to a very important part in summarizing data, perhaps the most important point, because most of the data summaries are actually given as a single number, and we call this number a measure of central tendency. It may be considered the typical value that the data takes, or it may be considered as the average value the data takes, and there is a subtle difference. So we'll be seeing what different kinds of averages we can take, and in which circumstances what kind of an average measure would be more appropriate. So we start our discussion about measures of central tendency by talking about mean. This is what most people think about when they think of average. This average can be calculated either from the probability density function, or given some observations we can calculate the average for it. So given some sample values, the taking of average is very common, and we, almost all of us would know it, because this is what we consider an average. You simply sum up all the values and divide it by the number of observations that you have. So this is known as the arithmetic mean. You also have geometric mean, in which all the observations are multiplied, and the product of all the observation, for example, if we have n observations, the product of these n observations, we take the nth root of that. But for this session, we are going to focus on arithmetic mean. We can also calculate the mean for a random variable. We shall see the case for both. As you can see on the slide, when x, the random variable, it takes discrete values, we make use of the probability mass function, and we take a sum of all the values which the random variable can take, and the probability of taking those values. If we have a continuous variable, we'd be taking an integral, but the idea is the same. It is the expected value which you will expect your variable to take if you were to conduct this experiment in finite number of times, let's say. So that would be the long-term average, or the expected value. It must be clear, or it must be understood, that this expected value is mathematical expectation. It may actually give you a value which you will never be able to get, but it gives you the long-term average. So it's important to understand this, and this is a common pitfall when we're talking of mean. A mean can give you a value which is not very typical of your population, and we'll explain this through an example. Let's talk about the performance of arithmetic mean for different kinds of distributions. So you can see this on the slide, that you have, for a symmetric distribution, the mean is the central point. So a mean is a good measure for a symmetric distribution because it gives us also the typical value. But for a bimodal distribution in which you have two peaks, the mean is the value in between, which is not indicative of the true nature of the population. Also, if you have a skewed distribution in which the tail is leaning either towards the left hand side or the right hand side, your mean would also be skewed towards the direction of the tail. Also, the arithmetic mean has a physical analogy. If you imagine the distribution to be created of some solid material, the mean would be the point at which this solid body would balance out. So now let me give you some examples, hopefully some interesting examples, which will make the points clear and memorable that when you should not be using the arithmetic mean. The first place where you should not be using the arithmetic mean is when you have a multimodal distribution. A multimodal distribution is a distribution in which you have two common values or multiple common values, and those are the modes of your distribution. So as an example to illustrate this, imagine a farm in which you only have horses and you have chickens. So if someone was to ask what is the average number of legs the animal on this farm has, the average value which will be calculated, assuming that the number of horses and the number of chickens are the same, would be 3. So this is the mathematical value, which is the arithmetic mean. अगर हम इसको analogy दे सकते हैं with the expected value of a random variable, you would have the same problem there. It is giving us a value which is not indicative of what will typically happen, and it does not quite reflect the true nature of the problem we are studying or the question we are asking. So we must be very careful when we are using arithmetic mean or the expected value in multimodal distributions. The other kind of distribution in which you should not be using arithmetic mean is when you have high variability. So to make this memorable, you can imagine an example in which a man has his head in the fridge and his feet in boiling water, a tub of boiling water. Would you call that this man is on average feeling okay? Obviously you will not, because he is in trouble on both sides. But the average value is the value in between, which seems to indicate that he is doing all right. So your data may actually be in a similar position. This is obviously a caricature of the real scenario. असल में scenario जो होंगे वो इतने ज़्यादा blunt नहीं होंगे, लेकिन you can generalize from this example. If you have a lot of variation, the central point may not be a good indicator of what the actual typical value is. Another case that you can imagine that an arithmetic mean will not work well is when you have the presence of outliers. Outliers are values which are very distant from the common pattern of data. So if you have a society, let's say a village society in which you have penniless paupers or very poor people having no money at all, and a multi-billionaire walks into this society, would you call that this society now has average income of 1 million? Obviously, this claim would be false, because this does not reflect the true reality. So if you have outliers in your data, arithmetic mean is always going to be skewed. So in such distributions, you should always consider the use of arithmetic mean as doubtful, and you should explore other options of measuring the central tendency. The last case in point is when you have categorical or discrete values that your variable can take, but your average may give you a value which is falling between the categories that can validly exist. So imagine a family, the average family. So if you calculate the average number of children a common family would have, this may come as a value which is falling between discrete number of children. So for example, you may say the average value that the typical Pakistani family has is 2.4 children. This is clearly wrong, because no family has 2.4 children. You either have 2 children or 3 children. So the use of arithmetic mean in such a case, when you can only have categorical data or discrete values, is also problematic. So you should always consider what mean you should use, and you should present a mean which the people are expecting as well. So if the people are expecting some other measure of mean, as we shall see, there are other measures of mean to measure typicalness of data variable or the typical value. So then you should present multiple means. So these examples, I hope, would clarify and make memorable the cases in which you should not be applying the arithmetic mean. Okay, now let's talk about the median. The median is a measure of central tendency which is resistant to outliers. because it does not take into account the values of particular observations, but it takes into account the relative ordering. So the median would be considered as the 50 percentile, which means 50% of the data would be above it and the remaining 50% would be below it. If you're considering observations and if you have even number of observations, it would be calculated as the mean of the middle 2 points. If you have odd number of data points, then this would be the middle data observation. So this is the median, and this is resistant to the outliers because regardless of the value of the outlier, it does not change the middle value. So in cases where you have skewed data, the choice of median would be more appropriate. So let's see how median works for the distributions of data for symmetric distributions, skewed and right skewed and left skewed distributions. So if you have a symmetric distribution, the median would be the same as the mean. If you have a right skewed distribution, your median would still be closer to the center or the typical value of data. The mean of the data would actually shift towards the direction of the skew. This is also the case for left skewed data, but the median would still remain closer to the typical central value. And also, if we were to consider, like we considered for the arithmetic mean, the physical analogy, इस केस में median वो होगा जो density curves को equal areas में divide कर रहा है. You have equal area on the right hand side of the median and equal area on the left hand side. इसको हम ऐसे भी समझ सकते हैं क्योंकि the area under the curve is defining the probability. The chances of data being on both sides of the median is the same. So 0.5 above the median and 0.5 probability below the median. We've already seen the median when we talk of the box plot, and the central value जो box and whisker plot हमने देखा था उसमें एक बीच में box बनता है, उसके अंदर जो बीच वाली line है, that is the 50 percentile or the median value. Another measure of central tendency is the what we call the mode, and modes are important when you're dealing with categorical data or when you have bimodal distribution. We've seen earlier that in computer networks we often have multimodal distributions. We gave an example of the distribution of packet sizes in which there are 3 modes. So in the case where you have multiple modes, the mean and the median is not a good indicator of the central value, but the mode actually indicates that what values are commonly occurring. And this is commonly used for categorical data as well. So for a skewed distribution के लिए क्या mode होगा? We've seen that the mean is actually skewed towards the direction of the longer tail. Median बीच में रहता है, लेकिन जो mode होगा वो highest value होगी of the density curve. If you're given some observations, उसमें से mode कैसे निकालना है? तो the way to do that is to find out the most common value, and the most common value would be the mode. As you can see on the slide, on the left hand side, because the value 3 is the most common, you would have the mode as the value 3. On the right hand side, you can see there are actually 2 modes, because both the value 2 and the value 6 are occurring most of the time. So we have 2 modes for this case. So let me wrap up this discussion then on the measures of central tendency by telling you which measure should we be using in which circumstance. So if you have categorical data, and categorical data, if you recall, is qualitative data in which the scale of measurement is to allocate the variable to a particular category. उस case में we cannot make use of mean and we cannot make use of median. So what we have to make use of is the mode value. If the total data is of interest, then you should always be using mean. But if the total is not of interest, and if you have a skewed distribution, you should be using the median. And the default case to which you would always fall back on is the mean value, because that is the value people expect when we are giving the average. So to summarize, I would say that it's very important that we realize that there is no single average measure, and we have to see what kind of data that we are looking at and accordingly select the best metric of central tendency. Let's talk now about the spread of data. So even when we know the central point of data, it's not that all of the data would actually be occurring at the central point. Data would be distributed around the center. In the case of a symmetric distribution, the data would be distributed in a symmetric sense around the center. But we need to ascertain and also report what is the amount of spread in data and how does it vary from the central point. So we've already studied, when we talked of the box and whisker plot, of two values which actually indicate the spread of data. The first value is actually the range of data, which tells us the value, the difference between the maximum value and the minimum value. You also have a measure called the interquartile range, which actually tells you the difference between the 75 percentile of the data and the 25 percentile of data. So it is telling you that the center is the 50 percentile, 25% of the data कहाँ lie करता है, उससे हम imagine कर सकते हैं कि data का spread कितना है. Also we can think of the 75 percentile in similar terms, and this tells you the spread of data. So these two measures actually do not depend on the distribution of data. इस वजह से हम इसको non-parametric कह सकते हैं. We also have parametric statistics that measure the spread of data, and these are very important in statistics because parametric statistics are commonly used, और जो normality की assumption हम लेते हैं उससे हमारी analysis बहुत ज़्यादा facilitate हो जाती है. So we need to understand these measures. So these are two measures which are very important. The first one is the variance and the second one is the standard deviation. So let's talk about variance first. Variance can be defined as the mean sum of squared errors. So usually the value would not occur exactly on the center. It would be a little far away from the center, and we can call this difference as the error. So we take the sum of errors for all the variables and then we square it. The reason for squaring is we don't want difference on one side and the difference on other side to cancel out. जब हम positive और negative difference का square ले लेंगे तो हमेशा आपकी जो sum of square errors हैं वो positive ही रहेंगे. So if we measure the variance around the mean as the mean sum of squared errors, we would call this the variance of the variable that we're studying. So variance can be calculated both from the density curve and also from the observations. So let's talk about calculating it from the density curve. So it is a simple formula. There are many automatic tools which will give you the answer. But to understand it, you can see the formulas written on the slide. So the value of xi and the difference of it from the mean is squared, and it is multiplied by the probability of that value occurring. So this is the variance of a discrete variable, and you have a similar definition in which we're taking integral for a continuous variable. You can also imagine variance being calculated for given observations, and it's important that we understand what are we using these observations for. अगर हम इस ऑब्जर्वेशन को सिर्फ इसलिए इस्तेमाल कर रहे हैं that we want to understand the sample, तो फिर उसकी जो हम वेरिएंस निकालेंगे उसके फॉर्मूला में जिस तरह आप देख सकते हैं डिनोमिनेटर में n है और n इस केस में बता रहा है कि the entire population. So when we are talking of variance of a population, इसका मतलब है we are not trying to infer or estimate something apart from the numbers that we have. But if we are using a sample, उसकी जो वेरिएंस अगर हमने इस्तेमाल करनी है एज एस्टिमेटर ऑफ द पॉपुलेशन पैरामीटर ऑफ वेरिएंस, then we must have n-1 where the smaller n is the size of your sample in the denominator. This is known as the Bessel's correction, and this is used to make the variance estimator unbiased, because it has been observed that if you have the value n in the denominator, जो variance sample variance आप इससे calculate करेंगे, it is going to be consistently less than the population variance. So to correct for that, we actually use n-1 in the denominator. So after having defined variance, we define the standard deviation, which is just the square root of the variance. And you can observe in this slide that you have two normal distributions. और जो sigma value है, where sigma defines the standard deviation, it is telling us how wide is the distribution, yeah, how much the usual data is varying around the center. If you have a more spread distribution, you would have a higher sigma value or a higher standard deviation. If you have a more narrow distribution, you have a smaller sigma value. Standard deviation is very important in parametric statistics because it helps us, because normal distribution has some very nice properties. Knowing just the mean value and the standard deviation, we can predict a lot about the population. So for that, we actually use a measure called the z-score, which only informs us that for a particular value, how far away is it from the center in terms of standard deviation. तो कोई भी value अगर x है, अगर हमने देखना है उसका z-score क्या है, तो हम उस x की value से mu को minus करेंगे, which is the mean value. वो difference बताएगा कि how far is that value from the center, and then we divide it or normalize it by the value of standard deviation. So this then tells us that this value is so far from the center, and then we have some empirical rules like for a normal distribution, 68% of all data would be in plus minus 1 standard deviation of the central mean. So we can use such empirical rules to actually learn a lot about population. You also have something known as the coefficient of variation, which is found out by dividing the sigma by the mean value, which provides us context that how big the standard deviation is as compared to the mean value. Lastly, I want to discuss that it is very important that we properly analyze the outliers. Usually, whenever we have outliers in data, and we define outliers as values which markedly differ from the usual pattern of data, this is indication usually of a bigger problem with your experimental setup, or it may be an indication that your hypothesis is not quite correct. So in both cases, we need to analyze the outlier. It is considered bad practice just to eliminate the outlier outright. Isme, again, this falls into the art of performance evaluation. If something is obviously wrong and out of place, then you may be right to remove that outlier. But aam taur pe outlier is an indication that maybe you have a bug in your simulation code, or maybe you were not very careful in writing your observations. So it is very important that we properly address outliers, and we also inspect our systems of taking observations and of our the software that we have, if the system is all right, because the outlier may be an indicator of problem with your system. So now let me conclude this session. I'll make two remarks about the usage of statistics. The first one is that we can use statistics to gather meaning from data, and the best mean of doing it is by plotting it and thereafter performing statistical analysis on it. And we can calculate many statistics from given data, but it's important that we use the appropriate statistic. In many cases, we cannot apply a particular statistical technique to a data that does not have the assumed distribution. So it's important that we only apply the tools where they are relevant. We'll discuss this more in future lectures. So I'll see you next time, inshallah. Assalamu alaikum.